Good afternoon. This is Lisa Clark, one of the reference librarians at the NOAA Central Library. I'm very excited to host today's library seminar titled Spatial Processes and Stock Assessment Methods. What has our group learned after 4 years of simulations? This presentation is part of the series National Stock Assessment Science Seminars, which is put out by NOAA Fisheries National Stock Assessment Program. Kristen Blackhart from NOAA Fisheries will introduce our 4 speakers, but before that, here are a few logistical tips to help you enjoy our presentation. If you're having trouble with the audio or visual components of GoToWebinar, please log out and rejoin the webinar. This usually resolves technical issues, but if you're still experiencing problems, let me know by sending me an email at library.seminars@noaa.gov. We'll also be accepting questions throughout the webinar, which the speakers will address at the end of the presentation. Please feel free to type your questions in the question box on the right side of your screen at any time. Also, this presentation is being recorded and will be available on the NOAA Central Library YouTube channel, as well as the library seminars website no later than tomorrow. The PowerPoint from today's presentation is available as a PDF in the handout section on the right. Please feel free to download it. So with that, I thank you for attending this library seminar, and I'm going to turn the presentation over to Kristen Blackhart.
Thanks, Lisa. Today, I'm really excited to introduce members from our Spatial Processes and Stock Assessment Methods group, an interregional effort to investigate impacts of spatial heterogeneity in population parameters on regional yield. There's been a lot of interest in these topics and the work from this group, so I've really been looking forward to this presentation. Our speakers today are Dan Goethel from the Alaska Fisheries Science Center, Amy Schueller from the Southeast Fisheries Science Center, and Brian Langseth and Aaron Berger from the Northwest Fisheries Science Center. Dan, go ahead and take it away.
Thanks, Kristen and Lisa. And thanks everyone for tuning in. Like the intro there kind of announced, we're going to kind of go over some lessons learned that are what we've termed informal NOAA spatial working group has come across over the last 3 or 4 years and some of the simulations that we've performed. Before I get started, it's kind of important. Whoops. Sorry about that. There we go. A little technical difficulty. So I just want to introduce kind of the rest of our members of the group. And first and foremost, Caitlin Bosley was the postdoc for all of this work. She was really the glue that held everything together. She's now the lead crustacean biologist for Puget Sound for the state of Washington. And she did a lot of cat herding and keeping us all in line and making sure the project was on schedule. As you heard, Brian, Amy, and Aaron are gonna present as well today. And then also John Doroba and Dana Hanselman were co-PIs. They weren't included in the talk. It wasn't personal, I don't think, but just want to show them. And then Carrie Fensky was also a key contributor. She really helped out with some of the sablefish case studies and kind of giving some insight from her sablefish spatial model. So just jumping into some background, why pursue spatial models? Well, kind of the basic ideas are that we can better address some of these fine scale dynamics that we observe in real world populations. At the same time, we can sort of better incorporate data at the scale that it's collected at, and that really helps us maximize the information content in some of that data. At the same time, I think once you start getting into looking at distributions and fine scale distributions, as well as accounting for movement and things like that, it really helps stakeholders really understand how their local observations kind of impact the larger population-wide stock. At the same time, you can start looking at matching the scale of management decisions, which is always important as spatial management becomes more widespread. And then I think ultimately the most important aspect is you really are able to explicitly address some of the assumptions that are either implicit or completely ignored in non-spatial models. And I really like this schematic here because to me, this sort of, the sweeping generality is sort of what you assume in this unit stock or panmictic stock concept, in that you really are assuming a homogeneous population throughout your entire modeled stock or population. We know that there's a lot of fine scale population dynamics going on in most fisheries and marine populations worldwide. And so when you start to address these explicitly, it really better reflects what is actually happening in the real world. So when we talk about spatial models, what do we mean? And really, we're trying to address kind of 4 of the main population structures that have been observed in marine populations. So the most basic and what's kind of the default for most assessment models is this panmictic assumption that assumes the entire population is homogeneous, has a single larval pool, all the population parameters are the same for all the individuals. And we know that this really isn't the case in most real world situations. Kind of the next step of complexity from there is this middle, or the second one here, spatial heterogeneity. And really what we have here is that there's kind of patches of population components spread out throughout the domain. We know these patches interact, and more or less it might be a single population. So a lot of the parameters, some of the demographics are kind of identical across the population. Usually we assume there's a single larval pool. And so it just allows you to address some of the patchy distribution that we often observe. And so an example of this would probably be like sablefish in Alaska, where we know that they can cover a lot of ground. A lot of the biological parameters are more or less consistent across a large geographic range. But especially for management and kind of harvest stocks, we know there's some differences in how they're harvested. So we might want to model that heterogeneity. Kind of the next level from here is the metapopulation concept. In this case, you have sort of unique subpopulations, each of which are more or less self-sustaining. So you have sort of these individual larval pools for each population. All the different populations may have different demographic rates, so you can model those separately. And then you have interactions between these subpopulations in terms of both adult movement and potentially larval drift. A good example of this would probably be herring populations or a lot of reef fish. And then kind of the final and most complex structure is this natal homing, otherwise known as home fidelity, or in terms of modeling, the overlap model, which is often used for bluefin tuna. And in this case, you have unique and discrete populations, spawning populations. They often have different demographic rates. They have their own kind of SSB and larval pool, but they may overlap spatial temporally in terms of maybe during feeding times. They may be harvested together, things like that. But fish, in order to spawn, they must return to their natal population. And so even though they overlap, they don't really add to the SSB of another population. And so kind of the goal of our study was to look at what are the impacts of either ignoring these population structures or misdiagnosing them, and can we incorporate these into an assessment model and still and get some robust results. So this last slide in terms of background is, this was put together by Aaron, and it's just a survey of NOAA stock assessment scientists. And it's really asking, do you observe spatial structure in the populations you model, and have you incorporated it? And a wide majority kind of responded with, yes, there is spatial structure, but we're not really sure how to go about it. And this really got us thinking, and at least me especially, I think a lot of this has to do with sort of institutional inertia in terms of moving towards these kind of more complex spatial models. It takes a lot of time just to develop the model, to validate it. And so there's a lot of difficulty in making that transition. And so our group was kind of focused on how do we, kind of improve the outlook of these relatively new spatial models make people a little less comfortable kind of using them. And so we kind of decided on this simulation framework. So we developed a completely generalized, spatially explicit simulation estimation model, and it's now termed the SPASM model. And so it's really flexible. It can do a lot of things. I think it's pretty unique and pretty interesting. It allows for any of those population structures that we just discussed. You can have any number of populations, regions, fleets. All the parameters can vary spatially: recruitment, movement, biological parameters, fishing, stuff like that. And then we have a lot of complex movement dynamics that we can incorporate both in the simulation and estimation model. If you're interested in kind of getting a full description, one of our papers about tagging data, incorporating tagging data into the framework is online. You can look at that one. And we have 2 GitHubs that you can kind of go in there and look at the code. And this is the only equation in the entire seminar, which I think is pretty good for a stock assessment seminar. And really what I wanted to point out is that accounting for movement in our case is we assume the box transfer method, which assumes at the beginning of a time step, the portion of the stock in a given area moves or stays resident. So it's just a fraction of the population either moves or stays where it is, so that the abundance in a given region, noted by the P subscript, after movement is just a summation of all the possible populations or areas of fish that either move into that area or stay in that area, multiplied by the abundance before movement. I won't get into the details of it too in depth, but that's sort of the basic background that I think you need to understand some of the stuff that follows. So we focused on 3 main areas in terms of kind of trying to push forward some of the spatial modeling aspects of stock assessment. The first one was looking at biological reference points. The second one was sort of looking at this assessment performance. And then the final one was what are some of the management implications, especially in terms of misaligning biological and management boundaries. So these are just 4 of the papers we have published so far. We'll talk about each of them kind of briefly, and then Amy and Aaron are talking about 2 more that are almost ready for submission. So that just gives you an idea of what we'll be talking about today. So I don't have a lot of time to talk about reference points, but I will kind of go over 2 of the first papers that we did that were sort of simulation studies. And the goals of these were just to kind of begin the conversation of how do we account for spatial structure in biological reference points, which is a lot of times kind of overlooked, I think. And so the main point being that we need to have this consistency from the assumptions in the assessment in terms of spatial dynamics through the management advice. So how do you account for those complex movement and population structures within, say, models of MSY and yield per recruit? And so for this study, we explored each of those population structures that we discussed earlier: the panmictic spatial heterogeneity, metapopulation, natal homing. And this complex graphic kind of shows the results in terms of MSY, harvest rate at MSY, SSB MSY for population 1, population 2, and the entire system. And the main take-home point here is that depending on your population structure and your movement, you can get very different sort of localized harvest rates and SSB associated with attaining MSY. And so this was especially noteworthy for some of the metapopulation structures. And so accounting for that is really going to be important as we start moving towards stock assessments that account for spatial structure. And one thing to note on this is we really viewed it as sort of a kind of a gateway paper to kind of introduce the kind of the concept, because there's a lot of issues we haven't really gotten into yet that need working out before we can really start using spatial models for management advice. And this includes accounting for like time varying movement in equilibrium models, and also how to deal with the movement of fish into and across population boundaries, and how that impacts, as they move into and out of new growth and mortality regimes, and how do you account for that in equilibrium models. So The second paper that Caitlin spearheaded took this a step further by developing a few more realistic case studies. So these results down here are yield curves for a sablefish model that we developed. This was a 3-area model. And on the right, we show kind of the yield curve comparing area 1, area 2. Yield is the color scheme, and on the right is no movement. On the left is when we incorporated movement. And really the take-home point that we saw from this was that when you have no movement, these yield curves are really steep and really pronounced, and you have this very limited combination of spatial harvest that will get you kind of the MSY from the system. When you start allowing fish to move across those boundaries, this kind of pronounced point now becomes sort of a plateau, and it really allows you to come up with a bunch of different harvest strategies that can still attain your maximum yield. And the importance of this, we think, is kind of from a socioeconomic perspective. Say area 2 may have more fishermen or stakeholders, or it's closer to shore, so there's more people accessing it and harvesting from that area, then it may allow you to kind of bump up the harvest of the quota for that area compared to area 1. And you could bump it down a little bit for that one and still kind of get your MSY. So I think it really opens up this whole concept of incorporating socioeconomics into your quota management. Caitlin goes into a lot more detail into things like allocating quotas spatially from panmictic models. So it's a really good paper, so I suggest you check that one out. And now I'm gonna switch to Amy, since I've taken up way too much time already. And hopefully she can take over.
Okay, can you guys see my screen okay?
Yep, we just, looks good. Just
It's taking a minute. Okay, so I'm going to talk about evaluating the consequences of misdiagnosing the population structure within an assessment, a spatial assessment model. And so, as Dan's already mentioned, there's plenty of evidence that we see as assessment scientists that suggests that stocks exhibit some degree of spatial heterogeneity, some degree of movement or connectivity among regions. And we see this in all kinds of species like tunas, herrings, menhaden, sablefish, etc. So this particular paper was interested in answering or trying to address 2 different questions. Can we obtain improved estimates for stock productivity by taking into account the spatial structure of spawning components and the connectivity between them or among them? And then what are the consequences if we misdiagnose the underlying population structure in our stock assessment? So what if we get our assessments wrong with respect to spatial structure? And so we based this paper on a case study for sablefish, and a lot of the data for this came from Dana Hanselman and Carrie Fensky, who are pictured here. And for sablefish, Carrie, this is a figure in the lower left corner of spawning biomass of sablefish in each of the 3 regions that are depicted on the map of Alaska here. And so 47% of spawning stock biomass being in the Western Gulf, including the Bering Sea and Aleutian Islands, 29% in the Central Gulf, and another 24% in the Eastern Gulf. Sablefish happens to have a 40+ year time series of tagging data to help inform movement. And so it was a great species and data sets to use for this case study. So because of the tagging information, we had time and age varying movement. And what's shown here in this figure is movement rate by age. So ages 1 to 16+ for areas 1 in row 1, 2, and 3 in each of the respective rows. And then it's showing the movement dynamics over time by year between the different regions. So on the top row there, that's area 1, the red line is depicting what stays within area 1, and then the green and blue are depicting what moves to the other 2 areas. In addition to that, our operating model for this case study also had variation in life history components. So for example, here's the maturity. This is the proportion mature, and it differs by area. So again, area 1 in red, area 2 in green, and area 3 in blue. We also had variation in recruitment apportionment, movement, fishing mortality rate, etc. So that was our case study. What did we actually do for this particular paper? What we did was we were simulating population dynamics for a bunch of different spatial structures. So we had several different true population dynamics, which is the top part of this figure, or several different operating models. And so we had, as Dan's described briefly already, the panmictic operating model, which is pretty much what we assume for most assessments and species right now. We have an operating model based on spatial heterogeneity, so differences occurring in life history parameters. And then we have an operating model that was a metapopulation model that had movement between differences in life history and impacts from recruitment differences. And what we did was we generated data from all of these different operating models that were then used to conduct multiple different types of assessments. And you see here I have match, mismatch highlighted. That's kind of the terminology we used. And so in a match scenario, for example, if we had a metapopulation operating model, then we would also have a metapopulation estimation or assessment model. But there were also scenarios where we had mismatch. So we could have a metapopulation operating model, but we're feeding those data into an estimation model that's based on spatial heterogeneity. And we did this with the eye of comparing the performance of those models and estimating the parameters that we assessment scientists are particularly interested in. And so the one I'm going to focus on today, just briefly, and some results are, or is, spawning stock biomass. So this is a relative percent difference in spawning stock biomass over time. And on the top there shows the 3 different operating models. So the panmictic, spatial heterogeneity, and the metapopulation operating models that created data that were then fit within a panmictic assessment model. And so the results show that the panmictic model generally performs pretty well, regardless of the operating model, but the fine scale dynamics are often getting lost. And so you'll notice towards the end of the time series, we're not doing too bad, but we definitely miss over the time series some of the ups and downs that we would have seen in the spatial heterogeneity and the metapopulation operating models if we use a panmictic stock assessment model. All right, to make things basically jump from the simplest example over to the most complex example that we had, I'm moving to a metapopulation operating model. And a metapopulation assessment model that we're looking at a match here. So there's a metapopulation operating model and a metapopulation assessment model that's on the right, and then on the left we're having a metapopulation operating model and a spatial heterogeneity assessment model, and so that would be called a mismatch. In each of these panels is the spawning stock biomass over time, and it's the relative percent difference in the spawning stock biomass over time. In the rows are areas 1, 2, and 3, and then the bottom row is the system level estimate of spawning stock biomass. In the columns are different tagging versions that we looked at. So if we had no tags, if we estimated constant movement, or if we estimated an age-based movement. The inset values here, those blue values, represent the mean absolute relative percent error. So models with constant movement and tags performed almost identically even when population structure was misspecified. And the correct population structure specification only slightly improved estimates relative to the mismatch scenario. So if you take a look at, for example, just the upper right panel in each of these figures, we're looking at differences here of 2.7 versus 2.5 when we have a misspecified estimation model. That being said, when assumptions regarding population structure are matched. The assessment model is much better at estimating movement. And so this is a look at estimation of movement in a mismatch versus a match example. And so we're looking at absolute difference in movement estimations for areas 1, 2, and 3 in the rows by age. And the closer the lines are, the orange, green, and purple lines are to the black dashed line that equates 0, the better job we're doing. So some general take-homes from this: the panmictic assessment models perform relatively well for estimating system-level biomass. Of course, they miss those finer scale spatial differences. When we're using spatial assessment models, it may be more important to correctly specify movement than to correctly specify population structure. The precision and accuracy in the parameter estimates are greatly improved when including tagging data, even when the population structure is misspecified. And finally, the estimation of movement improves when true and assumed population structures match. And overall, the big take home is generally misspecification of population structure can be overcome with good and correct assumptions regarding movement, or having some good tagging information to get at what those movements should be. All of this work is in a paper that's being put together right now, and so this is something to look forward to, hopefully in the relatively near future. Next, I will pass this on to Brian.
Thanks, Amy. Start from here. This is continuing on the assessment performance explorations. This is a paper that is currently in press, focusing mostly on movement parameterizations in spatial models. There is some element to tagging, but much of this section will deal with movement. And this came about through just our observations that a lot of the movement dynamics of the stocks that members of our group work on are either very seasonally or are age-based. And given these complexities, be it Pacific hake on the west coast with the leftmost figure, sablefish in Alaska in the middle, or Atlantic menhaden there on the right, there's complexities that can be modeled. And so our specific question was to look at how accurate these ontogenetic or climate kind of temporal variation movement needs to be incorporated and parameterized within our spatial models. So we looked at 3 sub-questions specifically. Do we need to estimate movement? How should we parameterize this movement within our models? And how much tagging data is needed, if at all? So I'm going to start actually with the take-home findings from this work, and then we'll move through and show some of the results that hopefully support these. We think they do. So the first one is not to ignore movement. The bias was less when movement is included in general, or when movement is not oversimplified. There are some scenarios that you'll see where ignoring movement actually performed better than other scenarios, but in general, estimating movement with some complexity improved model results. The second take-home finding is to estimate movement in blocks. We did 2-year blocks, but it could be different years. This is especially useful when the underlying movement dynamics are unknown. And then lastly, tagging data doesn't need to be available every year. We looked at across a couple scenarios and showed that intermittent long-term tagging is useful and does fairly well compared to annual tagging. So the methods for this work, as Dan described, were a simulation estimation model. Both models were a metapopulation model, and the operating model scenarios are shown here in the lower left. We then tested those with estimation model scenarios, 6 there for a total of 24 scenarios. And then we tested it under a set of 4 sensitivities. We used a relatively fast-growing, short-lived species, 8 age classes, 30 time year series. And for tagging, we had 5,000 tags released every 5 years. We'll go through the operating model scenarios here shortly. I just wanted to point out the estimation model scenario. So ignore meaning we don't estimate movement. Constant being it's the same across all ages and all years. Age-based time varying is fairly self-explanatory, and then either blocking it on an annual basis, estimating it every year, or on a biannual basis. The sensitivities, I'll talk a little bit about the tagging sensitivities, but we tested this with a longer-lived species, kind of simulating more of a groundfish-like species and a shorter-lived species, more of a short-lived pelagic schooling species. And these sensitivities were the model results are pretty insensitive to these sensitivities. So I won't talk more about that. The operating movement scenarios, I have simplified schematics here. We estimated these every year for every age, but for the sake of presenting, I'm showing just an early period, a late period, and then a juvenile population and an adult population. The kind of dotted boxes within these figures, population 1 and population 2, are the 2 metapopulations. So for our density dependent movement, fairly self-explanatory, kind of homogenized over time as fish move away from more densely populated areas. For the ontogenetic movement, here we're preferentially sending juveniles to population 2 and adults to population 1, indicating some age-based movement and preference. For the climate-induced movement, we are sending all ages to population 1 over time, indicating kind of this unidirectional movement. And then the 4th scenario is a combination of B and C. What this kind of eventually runs down to is that the juveniles go to population 2 less over time compared to scenario B, the ontogenetic scenario, and the adults go to population 1 even more over time. So those are operating model scenarios. The results to support kind of our take-home findings of including movement. Here I'm showing percent relative difference for population 1 and 2 in the top and middle rows, and then the system level biomass in the bottom row. Each of our operating model scenarios are the columns, and this is when we are not estimating movement. As you can see, some of the subpopulations aren't estimated with much bias, but the system level abundance is. And I should say the performance metric here is spawning stock biomass. Whereas for ontogenetic or the combined climate and ontogenetic movement scenarios, we're getting quite a bit of bias. If we compare these to the bias from the models with the best performing estimation model scenario, you can see when we're including movement, the bias is much lower. That is kind of the take-home point with this. I'll just stay on this for a little bit for people to be able to see. But when we incorporate movement, our bias can improve. The next set of results is blocking parameters. I'll go over this table. This is the median absolute relative error of biomass in the terminal year. Our estimation model parameters, or sorry, scenarios are now the rows, and our operating model scenarios are the columns. The light gray bars indicate the estimation model scenarios that had the lowest bias, so these were the best performing scenarios. And then we looked across all of these scenarios to see which scenario is the least worst scenario. So this is the dark gray banding where we're estimating movement in 2-year chunks. And if we look at the individual values of these for the density dependent model, all of these scenarios perform relatively well, except not estimating movement. For the ontogenetic scenario, the best one is age-based, and a close second is the min-max solution. Actually performs pretty close. Just pointing out here as well that our no movement scenario performed poorly, but there were other scenarios that performed even worse. The climate and ontogenetic ones. Climate, if you were able to get the general dynamics, the movement dynamics accurately estimated, bias wasn't too bad compared to other scenarios. And what this really shows is some secondary results is to beware the unidirectional movement. In the climate scenario, we could estimate it so that the bias wasn't too bad, but in some situations, if we didn't get it right, then the bias, and particularly in subpopulation 2, really was pretty poor. And then the other secondary result is that for ontogenetic, an age-based estimation scenario was best, whereas for climate, yearly based estimation was correct. And so you want to try to match movement to your primary axis of connectivity if at all possible. But if you don't know that, then blocking year and age movement estimation works pretty well. And then the last conclusion for this is gaps in tagging data are okay. So not tagging every year. Our base model was tagging every 5 years, and that's shown in the second and the fifth columns. We looked at comparing that to a no tag scenario versus an annual tag scenario. And annual performs best, but the 5-year tag scenario does not perform too poorly. The spikes that you see are due to the model having limited information in years where tagging is not available, and then gaining that information back and kind of being able to estimate and reduce the bias in your estimations for that 5th year. So with that, just again, respecifying our conclusion, it is helpful to estimate movement in most cases. How do we parameterize it? You can use intermediate complexity, particularly when you don't know what the primary axis of movement is. If you do, then try to match that. How much tagging data is needed? It might be more cost efficient to perform periodic tagging compared to annual tagging. In a previous paper that we had that Dan mentioned, we found that doing it regularly over a longer period of time does better than blocking it in intense intervals. And then lastly, just beware one-way unidirectional. So with that, I'm going to turn it over to Aaron.
All right, thanks, Brian. Let me get this to full screen. There we go. Okay, yeah, so this part of the talk, I'll be focusing on our management boundary analyses using the same operating and estimation model framework that we've already been discussing. So we developed this research question following on from other work investigating the influence of population boundaries and the scale of management action. In particular, we wanted to evaluate how bias and risk arise at different levels of boundary incoherence or boundary misalignment. And to do that, we looked at potential impacts from this incoherence across 3 different perspectives. The first one is an ecological perspective where unique aspects of each heterogeneous population component was of importance to manage. So for example, things like different life history rates, or even things like evolutionary significant units as with salmon. The second one is an estimation perspective where the misaligned assessment area itself is of importance. So for example, how well does the stock assessment model do? And the third perspective we took is a harvest one, where we are interested in localized depletion or underutilization as being an important aspect as it relates to regional total allowable catches, or TACs. To evaluate these different perspectives, a simulation study design was built using a 2-area box model, and this design included 3 main components to it. The first one was alternative sources of true spatial heterogeneity in the operating model areas, Area 1 and Area 2, including combinations of spatial differences in maturity, growth, or fishery selectivity, where these parameters were selected from or to be similar to Atlantic herring or Atlantic herring-like. The second component in the operating model was including scenarios with alternative levels of movement and recruitment apportionment as forms of connectivity in the operating model. The third part of it was including the incoherent or misaligned estimation models, and these were misaligned well, they were not a misaligned, so a 0% misalignment, or misaligned at 10, 20, 35, or 50% misalignment relative to the true operating model areas. So for the ecological perspective, we compared the 2 misaligned estimation area estimates to the 2 true operating model area estimates. For the assessment perspective, we again used the 2 misaligned estimation area estimates, but this time we compared them to the misaligned operating model aggregated estimates. So for example, we're looking at, from an estimation perspective, we would have an estimation model for Area 1 that would be slightly misaligned according to this percentage, so it'd be a smaller area. And in Area 2, the alignment would result in the full Area 2 operating model area plus this addition of Area 1. So the data or the information that was used would be averaged over between the 2 areas. And then lastly, for the harvest perspective, we compared the 3 misaligned estimation sub-area estimates. And by sub-area, I mean these areas that arise between the operating and estimation model areas as a result of this misalignment. So we have Area 1 gets split up into Area 1A, and then depending on the degree of misalignment, there's an Area 1B, which includes information in the estimation model from both Area 2 and Area 1. And then you have Area 2 just itself. So these sub-areas that arise as a result of this interaction. And then finally, the simulations included 75 overall scenarios, each run 500 times over a 30-year time horizon, and included process error in recruitment and fishing mortality, as well as observation error in catch and survey indices. And then we used the medium relative error in terminal year spawning stock biomass and total allowable catch, TAC, as these were used as our summary metrics. In terms of results, this figure shows the median relative error by area across levels of boundary incoherence from 0 to 50%, where the standard box plots here show an aggregation of all the scenarios. So those with different sources of heterogeneity and connectivity dynamics, just as a summary, within those levels of incoherence. Starting with the red boxes, which is a summary result of our ecological perspective analysis, as expected, there is a clear bias in the spawning stock biomass relative to the true unique population component. And that bias increases with the degree of boundary incoherence to a point where there are large discrepancies when the population unit is misaligned with the estimation area. There's also increased variability associated with Area 2 because that is the estimation area that includes data from the incorrect population component. Now the blue boxes show a summary from the estimation perspective analysis. Here, estimation is relatively unbiased in Area 1, shown over on the left side here, the blue boxes, because the data from that area is still representative of the population component, such that the quality of information isn't changing with boundary incoherence, just having less data. Whereas on the other hand, bias does increase with boundary incoherence for area 2 in this case, where data are essentially a weighted average from 2 unique areas, depending on how misaligned the boundary is or was. Overall, there was less discrepancies when estimation of spawning stock biomass alone was the goal. And now in terms of a regional harvest perspective analysis that we did, here are the lines that I'm showing in each panel are the median relative error by sub-area associated with the total allowable catch for that area across levels of boundary incoherence. The shading is 25 and 75% quantiles, and each panel here is a different scenario, including spatial structure due to maturity, growth, selectivity, all three of those combined. And you'll notice the shading here represents that the scale is, the y-axis scale is different than the other ones, as well as the inclusion of recruitment and movement connectivity dynamics. Here, recruitment in this example is apportioned at 60% to area 1 and 40% to area 2. And then the movement scenarios, for example, show in this case movement from area 1 to 2 of 10% of the population. And we looked at different setups or scenarios with those values. And in general, I guess there is an increase in terms of results in bias with boundary incoherence, but that is not always the case when connectivity is not accurately accounted for. So for example, area 1A, which is the red line, had the least amount of bias associated with it, as it was the area, as I mentioned before, with reduced but correct data. There were trade-offs between bias in area 1B, the maroon line, and area 2, the blue line, because these areas bore the brunt of the intersection between the true operating model dynamics and those blurred or contaminated due to the misalignment of boundaries. And the amount of trade-off or level of regional depletion or underutilization depended on the specific situation. Clearly, when there is unknown connectivity dynamics between areas, the potential for increased error in total allowable catch advice was heightened. So in terms of conclusions from this aspect of our work, aligning management areas with underlying population structure was particularly important. And we've noticed this in this work as well as aspects of our other projects that have already been discussed. These include fishing mortality, or particularly when fishing mortality is disproportionate to vulnerable biomass among areas, or when demographic data aren't homogeneous, or connectivity unknowingly exists among areas. Consequences for misaligned boundaries depend on your perspective. So for example, the work we've done, we took an ecological and estimation and a harvest perspective, and the results depended on which kind of perspective you were looking at. And so we think that these things should be considered and related to specific management objectives in operational contexts. Okay, that's all I have for the boundary aspect summary of what we've been doing. I want to take a minute now to just provide a summary of what some of the things we've learned from all that we've discussed today. So it is clear that the usefulness of spatial assessment models is context specific, depending on the goals of management and the availability of spatially sourced data. Oftentimes a management strategy evaluation approach is needed to aid in such usefulness decisions. The first steps to identifying and reducing the potential impacts from incorrectly specifying population structure is to understand the scale of population units, match those scales to the needs of management, and then utilize all the data available. Incorporating spatial structure and connectivity dynamics can result in a variety of sustainable harvest strategies, creating further options for adaptable management procedures. And then from a biological reference points perspective, more work is needed to identify appropriate reference points, at least at the scale, the spatial scale needed for management, which is not always a system-wide reference point, while maintaining cohesiveness between and across the stock assessment and management framework. For management and tagging estimation, correctly specifying movement may be more important than correctly specifying population structure. At least for data-rich situations, movement can be estimated without tagging data, but consideration of correlation structure is warranted. In general, when tagging, intermediately complex tagging designs can be sufficient while still remaining cost-effective. However, one-way population shifts likely require additional information. And as I just discussed, the consequences of misaligned boundaries are specific to the goals of management and the degree of boundary incoherence. And management strategy evaluation is again a useful tool and recommended for examining the robustness of alternative states of nature for operational considerations, or when such differences want to be evaluated relative to a specific case. There are several data, model, and management related needs at the forefront for improving the use of spatial models for management, many of which can be and are being overcome. And one of the main goals of our SPASM project was to develop approaches that lead to increased exposure of spatial procedures to overcome institutional inertia, as Dan mentioned earlier, associated with status quo procedures. Further, there is a need in the future to integrate alternative spatial modeling approaches, such as the concomitant use of species distribution models with demographically structured models, to integrate fine-scale spatial variance with management unit scale operational procedures. Again, management strategy evaluation is an excellent tool for examining such integrations for specific cases. In terms of future work for our SPASM project, we would like to transition our simulation framework into a spatial MSC management strategy evaluation tool. We'd also like to expand it or add modules to look at spatially integrated life cycle models, incorporating an IBM to help early life history and recruitment dynamics, the estimation of those. We'd like to include random effects, as those are advantageous in different estimation procedures, not rather including those that include spatial effects. We'd like to implement the model in real world applications and continue with international collaboration, such as the COCOCHA one here that I have listed. I wanted to quickly mention, I know I'm running out of time, but just quickly, an upcoming opportunities for you all on the line to get involved. So there's some upcoming opportunities include sharing your spatial modeling research or other population dynamics modeling research at the Land of Plenty, or the aptly named Land of Plenty Multi-Symposium Mini Conference really at the now 2021 World Fisheries Congress in Adelaide, Australia. And for those that really want to get their feet wet, there is a spatial workshop now planned in conjunction with the 2021 World Fisheries Congress to assimilate international approaches and advances through both expert presentations and discussion from global researchers involved with a simulation analysis study leading up to the workshop. So please feel free to contact myself or Dan Goethel. Our emails are on these flyers if you would like to learn more about either of these opportunities. For acknowledgements, funding for this work was provided by the previously named NOAA SAM project, or RFP. We also would like to offer special acknowledgements to Steve Cadron and the late Terry Quinn for mentorship and guidance on all things spatial, and to our project's postdoc scholar, Caitlin Bosley, who, having handled this group, can clearly achieve anything she puts her mind to. I will end the presentation here after passing on our team's gratitude and thanks to Lisa and Kristen for making this seminar possible. Thanks very much.
Thank you so much, Aaron. That's wonderful. So we have about 6 minutes for Q&A. And audience, I encourage you to go ahead and enter your questions in the questions box on the right. Our speakers are going to address all the questions until 4 o'clock, but if you enter a question and we have to end the presentation, we're happy to address your questions offline. I will make sure that they get them. So I do see one question here. Let me read that out loud. One moment, please. Okay. So this first question says, excellent seminar, thank you. You focused on tagging data, but genetics can also be used to understand spatial dynamics and structuring. Are any of your models flexible enough to include spatial data based on genetics? Have you considered using genetic data or collaborating with groups studying fish genetic structure to adapt the spatial models? What kind of information would be needed to do so?
Yeah, thanks for that question. I think our SPASM model doesn't have an explicit component currently for incorporating genetic data itself as in raw genetic data, but the products of genetic data in terms of spatial structure, movement, etc., could easily be incorporated into what we have. So the answer to that is yes, but to adapt it to be specific or have a separate module that uses an estimation procedure or a genetic or the estimation procedure within a genetic framework to then be used within our framework such that you don't lose the the variability associated with the estimates from the genetics. I guess what I'm saying is we do have the opportunity to do that, but a specific module to add that in isn't in there right now. Let me also ask either Dan or Brian to chime in here if they have anything additional to add.
Yeah, this is Dan. All I would add is that, especially with the natal homing model, which we haven't really dug into too deeply, there's a lot of opportunity to incorporate like species composition of the catch or the survey, coming from either genetic data or like otolith microchemistry data, and kind of incorporating that to figure out, what's the population composition of the catch. And so we have the ability to incorporate kind of that post-analyzed data. So, I mean, there are opportunities to use that kind of stuff, and we're hoping to get into that in the future. So we're definitely, I think, interested in teaming with anyone that would like to, go down that route and try to see how we can better utilize genetic data.
Great. We have another question. When should tagging be performed? During natal homing or on the feeding grounds?
Well, that's a great question. I'm going to pass that one again to Dan or Brian, who presented on the tagging aspects.
I guess I can try again. I'm not sure we really have an answer for that one. I think I could see benefits to doing it either way, or maybe even having a mixture of that. Especially if you have a natal homing scenario, I would think that being able to get some of that genetic data in terms of trying to figure out what population you're actually tagging, especially if it's during feeding and mixing, would be necessary. But I mean, I don't think we haven't explored that enough to have any definitive answers to the question, really.
Yeah, this is Brian. I would agree with Dan in terms of whether it should or shouldn't. For our movement paper, we incorporated tagging actually in the spawning grounds, and then the fish moved to the feeding grounds, mixed, and then moved back to their populations. And so we haven't looked specifically at the effects of either mixing or spawning populations, but for metapopulation, it's pretty similar.
Great. So we have time for one last question. And I do see that there are other questions as well, but I encourage you to keep asking questions because they will be forwarded to our speakers. Our last question is, how do closed areas affect model performance if you cannot retrieve the tags?
Well, tagging is a popular one, so I'm going to go back to our tagging folks. Dan or Brian?
Yeah, I mean, that's kind of a tough one. If you can't retrieve them, then you're really just reducing the amount of information generally. And it also depends on the type of tagging, because we have the ability to incorporate satellite tagging, acoustic tagging and things like that, in which case you don't really need to recover the fish itself. So I would say that in terms of things like closed areas, starting to transition towards those types of electronic tags would probably be really helpful. But I'm not, it's one of those things that we'd have to look at that explicitly to have a definitive answer, I guess.
And Dan, did we also, I mean, it's similar to tag shedding. The tag falls off, you're not able to access the tag, although the fish is still there. And we did look at that in the 2019 Fisheries research paper. I forget the results since I'm asking you if you recall what the impacts on that were.
Well, I mean, it's hard to say because if it's a closed area and there's no fishing and the model knows that there's no fishing in that area, then I would expect that you wouldn't really have a bias in those estimates because you're accounting for the fact that there's no fishing and therefore no tag returns, which is different from if you have tag loss or tag mortality and you don't account for it, because then you're implicitly forcing a bias into the model by not accounting for those losses. So I think it's a little bit different, and it's kind of hard to just come up off the top of our heads what the impact might be.
All right. Well, that last question concludes the hour. If your question was not addressed today, do not worry, we're not ignoring it. All questions will be sent to Dan, Amy, Brian, Aaron, and Kristen, who can respond offline. Just a reminder that this webinar was recorded, so feel free to share the link with your colleagues who might be interested in it. You can find it on the NOAA Central Library YouTube channel or the Library Seminars webpage. Are there any last comments from the speakers? No? Okay. Well, then I'd like to conclude by thanking Dan and Amy, Brian and Aaron for sharing their research with us today, and to Kristen for setting up the seminar. And to the audience, I truly appreciate that you joined us for today's library seminar. We're proud to present the work of the NOAA community, and we hope you will join us again. So be well, everyone. Bye-bye.